Okay, it's a minute past 11 Pacific time. Thanks for joining, everyone. Let's go ahead and get started. We should have a big turnout today. Today we'll be seeing a presentation by Marty Kandes, one of SDSC's computational and data science research specialists, on an introduction to Singularity, containers for scientific and high performance computing. But before we get started, I want to make sure we point out the XSEDE code of conduct. Everyone's usually on their best behavior, but if you do observe any inappropriate behavior, please submit a report to XSEDE.org/code of conduct. And also, in the interests of fostering inclusion and showing respect for everyone, we want to be sensitive to terminology in the following presentation or slides. So please report anything that you're concerned with to terminology@xsede.org as well. And with that, I will go ahead and hand it off to Marty.
All right, Jeff, can you see my screen?
Yes, looks good.
Okay, great. Okay, all right, hi everybody. Thanks for coming. Let me see if I can move this stuff out of the Zoom. Thanks for coming today to the XSEDE webinar, Introduction to Singularity. We're going to talk about what Singularity is, what a container platform is, and how it's useful for doing scientific and high performance computing, and sort of how you can possibly integrate this technology into your own research and computational workflows in the future. I've been giving this talk for a couple years now, and this is the first time I sort of tried to start rehashing it. Singularity, the software we'll talk about today, has gone through some changes over the last few years, moving from sort of major version releases, Singularity 2 to 3. And there's been a significant number of changes from Singularity 2 to Singularity 3, including sort of a push by the Singularity developers to commercialize the software, added a bunch of new features that even I'm not completely familiar with yet. But so I thought it was appropriate this time to start sort of rethinking the presentation here. The previous talks, which you might be able to find in still recordings for online, were aimed at really getting to some of the nuts and bolts of how to use Singularity and show some examples of how to build containers and run them on HPC systems such as Comet and now Expanse at SDSC. But all of the XSEDE systems have Singularity. So the aim of this talk now that I've sort of made, it's a little different. Instead of sort of trying to teach you exactly all the commands that you would use to go build a Singularity container and run it, I sort of wanted to more have this talk be an inspiration for your own exploration of, if you know, sort of, it's more of a pitch to why you should think about using Singularity if it fits with your use case, and why it's an important technology to sort of understand that's out there that you could use if you need it for your use case. In general, another reason for the redesign here is it's really difficult to do sort of live demos and make everything work within an hour. And so I thought sort of structuring it this way would be a little bit better. And I'll talk about that briefly a bit more. So let's go ahead and get started for today. Just make sure I can double check my time. Okay, so as Jeff mentioned, there's the XSEDE code conduct. I have these in the slides, but we can skip that. So today, what I really want you to take away from the talk is answers to these three questions for yourself. What is a container, if you're not familiar with what a container is? What is Singularity, and what Singularity can do for you, okay? And the idea, again, with redesigning the talk for today was, I have some ideas about, you know, how we can, if you are interested in Singularity, more of the nuts and bolts details and more advanced features of Singularity, there's sort of, you know, two other talks I can think about really creating, which would be sort of the follow on to this introduction talk, would be sort of how to create a containerized workflow with Singularity. Walk through all the steps that you would need to understand to really build containers yourself and run them, with, but before you do that, you really have to understand some of the basic concepts and definitions, and that's really what today is about, and like what's possible essentially, right? And then there's more advanced features now in Singularity 3, such as encryption and verification, sort of integrity checking with, you can actually sign the containers, upload them to different registries, and there's a whole bunch of other things you can do with Singularity now that you couldn't really do with Singularity in the version 2 series, essentially. And so there's a bunch of other topics here that you can dig into, and we just really don't have time today. So this talk, again, is really just about to inspire you to maybe want to become a Singularity pro here. And so so these talks are things I'm thinking about for the future, such as our Summer Institute. So you might see an advertisement for the Summer Institute. This is sort of a week-long HPC forum that we put on. And so one of these more in-depth talks will probably be part of that curriculum. So if you're interested in this material today, you might want to check out that more advanced stuff later on this year. Okay, so let's talk about containers. So if you start learning about containers and you maybe watch some talks by people, there's always one analogy that people give to sort of prompt people to understand the concept of what containers are useful in the software world. And it comes from a very different place in the physical world. And so this is sort of a leading question, but basically, I would ask, what can hold 10,000 iPads and travel from Shanghai to Hamburg for approximately $500? And the answer is a shipping container, right? So a shipping container is somewhat of a modern invention, right? It was really invented in its modern form in the 1950s. So it's only about 70 or so years old, right? But it transformed the way that modern freight shipping is done around the world and created the rise of globalization around the world, essentially. Because before shipping containers were invented in this sort of standardized box that can fit on a ship, a plane, a boat, a truck, a train, you had a very different situation, right? You had what was called bulk break cargo, essentially. So before containerization in the shipping world, you had essentially goods were loaded and unloaded individually, mostly by hand, from warehouses that the manufacturers brought their goods to the warehouses. They sat in the warehouses at the dock. Then once the ship arrived, they loaded the goods into the holds of the ships. And this whole process was really inefficient. And back in the day, most of the time, the ships would actually be in dock more than they would be sailing, right? So you spent a lot of time handling the goods themselves. And this could create problems like insecurity, where if you have a lot of goods sitting around for a while being handled by a lot of people, there's a higher potential for loss or theft of goods as well. And this whole inefficient, insecure process costed more, right? And so really you would only have shipping of goods from manufacturers locally, essentially. You could only really afford to ship luxury or specialty goods that fetched a high price, could really be shipped from long distances, right? But after containerization, you had this modern infrastructure created, essentially. You had a standardized shipping container that you knew the dimensions of. Everyone in the world basically has the same standard for what the size of a shipping container is, what the permissible weight tolerances are. This allows you to efficiently load and unload the containers, and they're more secure. Basically, you can send the container to the manufacturer. They can load whatever they want into the container that needs to get to the end customer. And the intermediaries who are transporting it, they might not even know what's in the container. All they need to know is how to move a container. You eliminate the process of this bespoke process of how do you move a bunch of barrels of wine versus a bunch of sacks of grain. There's different loading and unloading process for those goods. But if you just have everything in a single standard, everybody knows how to move that single thing, right? And this created a much more effective way of shipping goods around the world. And you can pretty much ship anything from anywhere for cheaper than it used to be, right? Now, so the question is, okay, so what does this have to do with computing? Well, when we talk about, what we do, right? I mean, we're, application developers, scientists. We want to run our code, get our work done, move data around, and we need to do that on different HPC systems. We need to do it, or we need to do it on our laptop. Maybe you have cloud credits that you want to run in a virtual machine on AWS. You have all these computing resources around you, and they're very different in certain ways. But at the end of the day, you want to run your code and against your data or generate your data with your code. But you have all these platforms that it needs to run on, right? Just like you have a bunch of different goods that need to get to different places, you can package your software in a container and move it around easily between these different systems. So the problem, the analogy here is really about software deployment, right? So this is looking at through time, right? You can imagine, obviously, just like shipping, computing and software has changed over time with the hardware that it runs on, right? Back in the day, you could, had to wire your software up, got a little bit better. Maybe you had some punch cards that you had to, print out and feed into a machine on a large mainframe that took a team of people to run your software. And eventually you had PC, and then now today you can just order your computing infrastructure from your command line on your laptop, right, out in the cloud, right? So the evolution of the hardware changes how you deploy the software, right? And that makes sense over time. But just today, right, on XSEDE, right, we have many different systems that you might have time allocated on, that you might want to run your software on. And even though these systems are very similar, from Comet to Stampede 2 to Bridges 2 and now Expanse at SDSC, right, they have very similar infrastructure, but each one is sort of still like those old those old sailing ships and cargo ships where they're all slightly different. Yeah, they're all meant to do the same thing. They all have, places to store things like software and libraries, but they're all slightly different sizes, and they don't run on all the exactly same software and libraries. And so that creates a problem for you when you have to compile your software on each of these systems and run it, right? Each time you bring your software into one of these systems, usually what most people are doing is recompiling their package to meet that will run on that hardware with the software that's been deployed there for them to support your application, right? And so this is one example that I did today. This is like a code that I wrote myself, and this is just this is one way I'm compiling it on Comet at SDSC, one way I'm compiling it on Stampede. And so I'm just downloading the code, right? I have a make file that I need to run, but first I need to check what sort of software modules are loaded, what operating system is available, what dependencies does Comet and the SDSC team here at SDSC provide on Comet versus, in this case, I'm looking at a compiler and a type of MPI. And then at Stampede 2, it's completely different, where they have, different default software modules available here. They have like an Intel compiler with Intel MPI. And you can see when I run the make command, eventually, once I have my sort of unique software environment for each machine, even the output from just compiling the software is different, right? In this case, it's not that big of a deal, but it's just to illustrate that just to compile the software, you have a different process on each machine. And then, of course, you can imagine once you have a different process of compiling it, running the software is going to be slightly different as well. Now, this is a fairly simple code, but some packages that you might be working with that maybe you didn't even write, they can be these huge, exascale project, codes that you want to use yourself have, hundreds, thousands of dependencies versus like the 2 dependencies that I have for this code essentially. Right. And that becomes really hard to satisfy when you move from machine to machine, right? Because each time you try to recompile things, it's going to be slightly different because there's different libraries that have been put there for you, different compilers, different MPI, different math libraries. And so it's kind of like the old bulk break cargo thing. We give you on each machine we run kind of a unique environment. You kind of have to figure out how to fit your goods into our platform, right? And so that's what containers are really for, right? So a software container is really, it's not a physical container there's not really a thing. So I put this Microsoft Windows thing here just because software used to come in an actual container. But in this case, a container, when we talk about it in terms of software, it's really more of an abstraction. There's not really a physical thing you could point to that's the container, right? It's really a set of technologies that allow you, that you bring together, that allow you to run software reliably when you move from one system to another. Okay. Now, there are things that we think of as containers when you start using them. The first one that you'll likely encounter when you start using containers is a container image. So a container image, which some people just, you'll just generally hear called a container because it's one sort of facet or instantiation of a container. It's really a collection of files that are just saved. It's either a file or a collection of files that are saved on disk and stores everything you need to run your target application or code on any system, essentially, right? So it has like source code, runtimes, system tools, libraries, etc., configuration files, whatever you need essentially to run a certain application, is associated with that file or set of files, which is called a container image. So the image here is just, so the actual image shown on the screen here is actually just listing some of the containers that we have on Comet here. So these are kind of the 2 most popular ones that we support essentially, because TensorFlow and PyTorch are hard to compile on the operating system that is usually run on HPC systems. They're very good candidates for using containerization. And so here you can see these are just, each of these files is a container image, right, that I'm listing here. Right, this is a different version of TensorFlow and PyTorch that run on GPUs and sort of have some dates attached to when they were created. But these are sort of container images, right? These are just files. So these are actually Singularity container images. Now, when you take one of those images and you want to run the application that it's sort of targeting, right, you run a container process essentially. So sometimes when people are talking about containers, they're really talking about container processes, right? And these are just standard Linux processes that are running on top of the host operating system and kernel on the hardware of the system that you're on. The difference is that inside the container, it's really an isolated software environment that's defined by the contents of the container image, right? And so inside that container, when sort of your application looks around inside the container, all it sees really is the environment that you've defined within that container, right? You can allow it to see outside the container. That's sort of, there's some options to do that when you're running these container platforms like Singularity, but essentially it's really just another process that you're running. So here I have an example where I've just taken our TensorFlow example. I've started it just like any other batch job. if you have access to Comet, you can go find that directory and take a look at the example. But essentially, it's just another batch job that I've submitted to Slurm, and I can go to the node on Comet, to the GPU that it's running on, and just see that I'm running. Okay, if you're not familiar, TensorFlow is a Python, usually interacted with through a Python interface. So here's my Python process that's running. That's the containerized Python process that was started from that batch job. And it looks like any other process that's running on these GPUs, where here in this case, I'm running on GPU number 3. It's really, it'll look exactly like any other process that you start on these systems. It's really, the only thing that's different is what the software environment around it, the container process, sees, right? And that's the unique thing. And this is kind of the analogy that I've used in the past, where if you've ever seen the movie The Matrix, they have, they go into this virtual world, and before they go into the virtual world, called the Matrix, right? So they have this thing called the construct, where basically it's the program that they run before they go into the virtual world to get all the supplies that they need before they go into the Matrix, right? So you can think about a container as this kind of loading program. It's where you're going to load all the software you need to run on any HPC system, on any supercomputer, or your laptop, or a cloud virtual machine on, say, AWS. And you could then bring that anywhere you need to go, right? Now, I've mentioned virtual machines, and so that might be what you're a bit more familiar with if you've used them in the past. And there's a fundamental difference between containers and virtual machines, and why containers are more interesting in, say, the HPC space, or basically any space. But containers, right, have really direct access to the underlying hardware through your kernel on the system, right? So if you're not familiar with how sort of a Linux operating system works, right? You have sort of a user space where your applications run, right? And all of the sort of utilities that you interact with sort of run user space, and those applications call to the Linux kernel, and that's the layer that really talks to the physical hardware, right? And so the containers are able to actually use the kernel on the host machine that you're running on, versus a virtual machine. A virtual machine, what it really does with this so-called hypervisor layer is it emulates the hardware, a hardware layer that your application's running on. So you have these additional layers of translation that are occurring when your application's running in a virtual machine versus a container, which would seem pretty obvious. If you have more layers of sort of abstraction and translation happening from your application running versus between you and the hardware, you're going to have a significant performance hit, right? Virtual machines can have significant performance overhead if you're running an application on them, versus a container is almost native performance. In most cases, you won't even be able to tell the difference, right? So that's one of the big advantages. So performance is definitely the biggest advantage of containerization, right? So, but it's versus, say, a virtual machine. But the next thing is the freedom. You can bring your own software environment wherever you go, right? You don't have to come to our team and ask, hey, can you compile this software for me? Can you put this software on the system? In some cases, you can't really containerize things, and we'll talk briefly about that. But in general, if you want to put anything you want into a container that will work for your workflow, you can do that, right? And so you can, and it should, and in general, there are some caveats. It will run on any system that supports that sort of container platform, such as Singularity, right? The other thing for scientific computing in general, right? Like one of the big topics in science in general is reproducibility, right? If you're running some simulations or doing some data analysis, and you run that analysis or run that simulation, say on Comet versus Stampede 2, you really hope if you put the same inputs, you get the same answer on both, right? But there's all these slightly different, software environments that you might have compiled against. Maybe one math library has a slight bug on one system versus the other, and you might get different results, right? So if you containerize your package, you at least have a snapshot of the exact software applications and dependencies you use to run a piece of software, right? Or an analysis or a simulation, right? And so it will always and should always reproduce the same output for the same input, because you have exactly the same applications and libraries that you've compiled them against, right? Or built your software against. And the last two, compatibility, Linux is, widely available on many different systems these days. And all of these container platforms that you've heard of, such as Docker, now Singularity, I mean, they're built on a similar set of standards that are sort of still forming, but widely used in both the research academic community, but also in industry, right? And of course, the portability aspect, right? Being able to build your application once and run it almost anywhere is kind of, again, the freedom to sort of bring your own environment and only have to do it once, essentially, right? Now, there are some limitations to containers, right? So architecture dependence does matter and the binary format of that architecture. So you can't, for example, take a container that you built on an x86 machine to an ARM machine, right? You're going to have to rebuild the container for the ARM architecture, right? Portability is somewhat limited sometimes, depending on, it can depend on sort of the versioning of the underlying C library and your kernel in the host versus the container. So for example, if you have a CentOS 6 machine, the kernel on a CentOS 6 system is too old to run, say, newer containers that are built with, say, an Ubuntu 2004 operating system in the container, right? So there is some kernel compatibility issues sometimes, depending if you get too far away. And also you can run into issues with hardware drivers is kind of where the real caveats come in. You have to have some sort of compatibility between hardware drivers that are either on the host systems you're running on and the ones that you have in the container. There's some solutions that are out there for getting around these a little bit easier these days, but in general, these are kind of some of the sticking points. And file system isolation, this is, I don't know if this is a limitation, but basically this is kind of another point. Like, right, the file system inside the container looks different than the one outside the container, which is understandable, but you can manipulate what the file system looks like on the inside. So for example, if you want to see your Lustre scratch space in a container on Comet, you can do that. You just have to add like another option basically to bind that sort of file system to your container. Right? Now, I've mentioned Docker. If you're not familiar with Docker, this is probably the most, if you have heard of a container platform before, it's kind of the most common one you've probably heard of. And this is really the first container platform that brought together all those different technologies that really made containerization popular. The problem for us is it was really designed for sort of network-centric services. It was really designed for industry, like, people running web servers and databases. And while it's easy to install, like well-developed documentation, there's a huge community out there. It's not really designed for HPC systems, right? HPC systems are shared resources, right? You can be running on the same node with other users running their scientific code right next to you, right? And Docker's security model doesn't really support this. It really assumes you have sort of trust between all users running on the systems. And in most HPC systems, the system administrators don't even trust the users, right? Because we don't allow you to have, say, root access or sudo access to install your own software that way, right? I mean, so you're probably familiar with that if you ever tried to sudo apt-get something onto one of the XSEDE systems, right? You can't do it, right? But also things like, Docker wasn't really designed to support, batch job schedulers or tightly coupled applications that need to communicate between lots of processes, such as, MPI applications. And so, when scientists were first asking, system administrators to, hey, we want to run Docker and do all this cool stuff on, HPC systems, it just really wasn't tenable, right? And there just wasn't really a path forward. And so that's what sort of inspired Singularity, right? It was designed from the ground up at Berkeley Lab to be the Docker essentially for HPC, like do all the things that containers can do in a way that allows them to run on supercomputers, essentially. But you get all the advantages of portability, easy to share and distribute and reproduce, the containerized software. The two things that are really different with Singularity is it allows this sort of no trust security model. So it fits in the HPC space by, allowing the container to run as you don't need root access to run the container. It's just sort of untrusted users can run untrusted containers on most HPC systems if Singularity is installed, right? So you can just build whatever you want in your container, upload it to Comet and run it, right? Or Expanse or any of the other XSEDE systems. And it was designed to, be compatible with HPC hardware like, high-speed networking like InfiniBand or, GPUs and, things like NPI, right? So these are some of the features of Singularity, which I've sort of touched upon probably already, but one thing that's different about Singularity versus, say, Docker, if you're familiar with Docker, is each container image file for Singularity is a single file, right? So there's not this whole layering structure that you find in Docker, which can be a good thing or a bad thing depending upon the situation. But the single image file is kind of nice. It's easy to share with, say, a collaborator. It's just, it's easy to keep track of all of your. It's easy to keep track of basically your software environment, right? You don't have all these different layers that might have dependencies that change if something gets patched, and it's nice. It's basically a static file that doesn't change. Once you build it, it's going to be the same file. It's not going to change. It's read only actually once you build it, and so it's sort of an immutable read only file that if you want to change it, you just build a new version of it. Right? Again, the security model. There's no sort of root owned processes. So there's no way for the user to change or escalate privileges to cause these security concerns that system administrators would be worried about. So it supports this shared sort of multi-tenant resource environments that you find at HPC centers, right? And of course, like as I mentioned, it supports things like InfiniBand, GPUs, and MPI. So the most common use cases that we see at SDSC are for using Singularity containers, beyond, I think hopefully what I've convinced you, the benefits of building your own environment and bringing it wherever you want, is what we use it for is usually to support applications that require newer system libraries than are available on the host system, right? And what I mean by that is, if right now we've recently deployed Expanse, and we're running one of the newest operating systems, CentOS 8, but we haven't deployed necessarily every single package that CentOS has in their repositories on the system. But we get requests from time to time for people like, oh, hey, can you install this? Can you install that? We can, but it's a process for upgrading. You can imagine, a few hundred or 1,000 nodes, thousands of nodes for the system administrators, right? There's a process that has to go on. So it's the turnaround time for requests like that. If you need something installed in the base OS of any operating system on an HPC system, right? That's kind of a lot of, it's not necessarily a lot of work, but it's a long process for that change to get pushed out to the system, right? So if you really need, software, you can, containers are one way to get that, right? You can build your own and just upload it and run it if you need like a piece of software, right? So, but sometimes when those requests come in, maybe we can't support those newer libraries because maybe the kernel version that's running the operating system isn't compatible with what you need. And as I mentioned earlier in the talk, two of the most common ones are sort of TensorFlow and PyTorch. A lot of the machine learning applications, right? These things are evolving really fast, and they usually assume you're using the latest and greatest operating system. And in both those cases, usually they assume you're running some sort of Debian-based Ubuntu operating system, which most HPC systems just aren't doing. And so there's a lot of incompatibilities, and it's not necessarily easy to compile those packages natively on those operating systems, right? And so that's what's our most common use case, I think, is what we use it for ourselves. Other cases might be like if you have an application that you pay for from a company, they might only be for your research. They may only give you a compiled binary, right? You might not have the source code, so you might not be able to build it. Your license agreement doesn't allow you to have access to any of that kind of stuff, right? And so, as again, those companies might be assuming you have a certain set of requirements and operating systems that we can't meet on those systems. Well, you can then use a container to package that binary with all of the things that the company says you need to have installed in your operating system. You can put it in your container and run it from that container, right? And then the last one is probably the second use case we see most common is people find some, have some existing Docker containers that maybe were developed, previously by the research group or, a collaborator, and you can't run the Docker containers directly on, say, Comet or Expanse, but you can convert a Docker container to a Singularity container with Singularity, right, and then run it. So those are kind of the three big ones. I think I would say. Now, sort of the last half of the talk here is really to sort of talk a little bit more about the nuts and bolts, but not go into too many details. So hopefully, sort of, I've inspired you to sort of get curious, at least to take a look at Singularity for maybe one of your use cases. But this is sort of how you use Singularity, kind of this last bit of the talk with some quick examples, essentially. But this is kind of the workflow to think about when you're talking about using Singularity and what you need to think about. Can you use Singularity? One of the key things is if you want to build your own custom container, you need to have root access to the system, essentially, right? You need to have a personal computer, a virtual machine, say, could be on, say, for example, XSEDE's Jetstream. You can get virtual machines there. Could be on AWS. But the biggest stumbling block I see people who are interested in Singularity but don't really go their own way of, say, building custom containers for their own workflow is they don't have access to a Linux machine where they have root, right? Usually, the majority of users have, say, a Mac or a Windows machine, and that's not necessarily going to work. You can work. I'll touch on briefly how you can get started with it. But ideally, it's not really the long-term solution necessarily for you if you really want to get serious about building custom containers and using them in your workflows. Because essentially, at the end of the day, actually building a container is, you're sort of maintaining a mini Linux operating system in the container. So you kind of need to get familiar with that sort of level of detail at some point, right? So this is the one stumbling block on some for some users, essentially, where you really need to build your containers elsewhere. There are some new features of Singularity which we have not tested yet. For example, at SDSC, and whether or not we would ever allow them. You could, in theory, build containers on Comet or Expanse or any XSEDE system, but right now I don't see that happening anytime in the near future. Maybe in the next year. I think I'm going to push for us to evaluate that, but that's a topic for one of the more advanced talks, essentially. So, but if you go down the route of wanting to build your own containers, this is the first requirement. You need to have somewhere to build them. And then all you have to do is, once you have your custom software environment built in your container, you just transfer that file to that Singularity container to the system you want to run on, and you run that container on the system. That's it, right? So the first part is the hard part. Now, there is a way to do this on your Mac or PC. The way that I recommend, the way that I've been doing recently, since my Linux laptop died and now I have a Mac, is you can install VirtualBox. So this is a virtual machine software from Oracle you can run pretty easily on your laptop or desktop. So I would definitely recommend checking it out if you're interested in playing around with Singularity or just Linux in general. You would install VirtualBox, create a virtual machine with your favorite Linux flavor, and then you can install Singularity on that machine and use it. And the recommendation here that I have at the star is just, if you're going to do that and actually run the containers on any of the XSEDE systems, the general rule of thumb is don't use a version of Singularity that's higher than the one that you want to run on the HPC systems. Essentially, there are still, like other software, Singularity is kind of evolving a little bit fast, and the backwards compatibility from the container image format sometimes breaks between versions if it's not you can't run a newer version necessarily. If you use a newer version of Singularity, you can't necessarily run that newer container from that newer version on an older version of Singularity. Maybe you can, but it's not guaranteed. And so these are probably kind of running out of time here. I might skip over this, but if there's 3 commands that you need to learn when you first get started with Singularity, it's these essential commands. It's sort of the build command, to build your own container. Shell sort of allows you to interact with your container. You can essentially log into your container and run the software interactively like you would on an interactive node, essentially. Or it's also useful when you're building containers to actually modify the containers on the fly if you need to, which isn't ideal, but it's a topic for another day. And then the exec command is this is what allows you to essentially execute arbitrary code within your containers, right? So anytime you want to run, say, your TensorFlow script, essentially you do a Singularity exec, Python, and then the name of the script that you want to run, right? It's how it's just the one command to run them all, essentially, right? So any command that you would just run on the command line, and essentially you can be fed into Singularity exec, and it'll execute. The only difference is it's executing it within the container that you specify. So, like I said, I think we're running a little longer than I wanted. So I'm going to skip over these commands. These slides will be posted with the talk eventually. So if you want to flip through them, you can check them out. Again, I mentioned that, I've given this talk several times, so you can find the old version of this talk where I probably went through more details of this kind of stuff in that version of the talk. If you want to take a look at those should be available on the SDSC website. So I'm going to skip over this for now, and it's just, again, this is my first pass through this new version. of the talk, so I still need to flesh it out a bit more. One thing I will mention is, okay, if you want to build Singularity containers, you need something called the definition file. This is sort of the manifest of everything that you want loaded into your container, right? So essentially it's, you can see here in this example, I'm doing a bunch of apt get install commands. Essentially, if you want to build a container from scratch, you have to write one of these definition files, right? And so this is where you put everything that you want installed in the container when you run that Singularity build command. This is how you specify it, right? And I have a repository here available on my GitHub that tracks all of the containers that we support on, say, Comet, and now they're sort of in the process of updating most of the containers for Expanse. And essentially it's just a collection of different definition files for different applications that you can check out. So they're good examples. Maybe the application that you want to use is in there and you just need to slightly modify the container to add a few more dependencies that you might need. For example, I often get the question is like, if someone's say using my TensorFlow container, they're like, oh, can you install this other package in it? Because it's not already in there. It's like, well, it's like, you know, I have to weigh the cost of, you know, how much time it takes to rebuild the container. Is this package going to be useful for other people? You know, if you want to modify your own version of our containers, this is, you know, the recommended way to do it. You know, learn how to build it yourself. You can modify, put anything else you want in those containers, right? So this is really base examples that you can start from, essentially. Or you can, if you have a request, you can send me a request if you think I need to add a library to one of them. So building containers, interacting with containers, running containers. Again, so there's a few caveats that I just need to touch on at the end here. If you have an MPI-based application, things like this is one of those caveats that where portability can become an issue. Right, and the fundamental thing that you need to keep in mind is that essentially you run a Singularity container with an MPI-based application the same you would natively on the system, right? You have to choose some flavor of compiler and MPI on the outside of the container, and that has to be compatible with the version you install inside the container, right? And then there's all these things. I mean, and then the system, if it's running with InfiniBand, you have to make sure that the drivers inside the container are compatible with the drivers outside the container on the host system. So if, you know, say Comet and Expanse have very different InfiniBand driver versions, you know, the container, if you take one from one system to another, it might not work out of the box. You might have to modify it slightly to get the MPI working. So this is one of those special cases that you need to, you know, take a little bit more care of if you're going to build containers for MPI-based applications. Let's skip over this. And it's a similar situation with GPU containers. However, Singularity now has really built-in options for GPUs, both NVIDIA and I guess now I haven't tried it myself, but AMD GPUs. So they have special flags now that allow you to sort of load the drivers from any system that you're on and use those from the underlying host system. So you don't necessarily have to match the same versions inside the containers. So if you go to my repo and actually get into some of the details of building containers, you'll see I do install like NVIDIA drivers and different versions of CUDA in some of these containers. I do that usually just to match our systems, but you could use those on any system if you do this sort of import method with these flags that allow you to bring the external driver modules essentially outside into the container when you run it. And I think I'll end here with 1 minute over what I wanted to go. But so this is kind of the summary for my pitch for Singularity for you if you're interested in learning more. It really is a way to install software that you need on any HP system without having to ask the system administrators or user support staff like me. I mean, we spend a lot of time installing and maintaining software for our users, and sometimes it takes us a long time because we have a lot of requests. And so if you learn how to use Singularity, like, you don't have to sit around and wait for those requests to get filled, or in some cases, we won't be able to fill them for certain reasons. But the nice thing about having Singularity, if you do it yourself with Singularity and it fits your model, your computational workflow, you don't have to go. I mean, asking for a piece of software just on Expanse and then Comet and then Bridges 2 and Stampede 2, right? Those are 3 sets of different people that have to do the same thing for you on these different systems. If you figured out how to do it once in Singularity, and it was exactly what you wanted, you could use that same container on all of those systems, right? That's kind of the key thing. This idea of portability and reproducibility on any system that you really want to run on, right? Yeah, and so that's kind of my pitch for Singularity. So we have a few more minutes left. I mean, that I can either take some questions or I don't know. Is Jeff?
So
yeah, there was a pretty good there was pretty good dialogue happening on the chat. Maybe Mary and Mahidar were being very helpful in handling those. Maybe they have something they want to bring to your attention that you may be able to help clarify.
Sure.
There was a question early on about whether there are instances in which a virtual machine is required or better than a container and things like that, but it's a fairly extensive chat. So Marty or Mary, do you think there's anything Mahi, anything that Marty should be aware of?
yeah, I think there's one that right at the end that I haven't looked at yet, and I think maybe Marty can comment on that. Have you looked at fake root?
Yeah. So yeah, no, that's a good question. So this is I sort of sidestepped this, but briefly alluded to it, that there is this way to in the newer versions of Singularity. I think it's particularly 3.6 and above that we would have to move to, which we're on, at least at SDSC, we're at 3.5. And I don't know, I haven't checked if Bridges, PSC and Stampede, I know they have Singularity 3.6 on their systems, and that should support the full fake root option for Singularity, which essentially for without going into too many details, it allows you sort of a fake root access to your container on a system where you have no root access. And so in theory, you can install or build your own containers on our systems. So if you don't have access to a Linux system, you want to say log into Expanse and build your own container on Expanse. In theory, we could do that with the newer versions of Singularity. However, this also requires special permission in the configurations of Singularity, which is why I don't know if I haven't checked if PSC and Stampede or the Intact folks support this yet. So it's an open question whether or not I think we'll support it for users in general. It really does require a specific special request at this point, and we have not evaluated it ourselves yet. So I would, yeah, it's a possibility down the road is what I would say, but it's not supported at this time at SDSC.
Yeah, there's another question there. Is there a repository in Singularity where already built images could be run later to save time?
Yes. So this is one part that I sort of need to get back into. I'll make some comments on this. Yes, so this is one topic I didn't touch on. So Singularity does support what we would call container registries, right? So these are essentially places where you can usually, the registry itself usually stores the containers. Usually they're attached to some sort of build service where you can actually take your definition file, this manifest of all the software you want, upload it to this sort of cloud service that will build the container and save it in the registry for you. And there are, if you go to Scilabs, is the company that's popular, that is commercializing Singularity, which started as sort of a research open source project at Berkeley Lab. Right, this is the company that is sort of commercializing it, and they do have services such as the container library, which is this container registry where you can find stored images, so you can browse what containers are available there. They also have a build service, so you can upload a build file there, a definition file, and get your container built. It's sort of a freemium model, so if you want to try it out, you create a login, you get, I think, 10 gigabytes of storage. I don't know how long. I mean, there's some limitation on the build service itself too. And so that's the Singularity sort of specific registry. So it's like Docker Hub for Singularity, right? There's also, I'll mention Singularity Hub, which is the sort of original registry and build service for Singularity. However, while I was working on this talk this last week and updating everything and getting familiar with Singularity 3, there was actually an email from the developer who and the admin who maintains Singularity Hub, and she's actually not going to be able to maintain it anymore. So it's sort of up in the air how long the Singularity Hub here will stay up. So it might go away this year, it might not. I think it's looking for a new home and a new caretaker. So so if you're anyway, so yeah, so there are Singularity container registries, and so you can find different collections of containers here. So I have a bunch of, if you go to my Naked Singularity project with the definition files, if you look at the README there, you'll actually see that I have a bunch of our base containers are built on Singularity Hub, so you can actually download those base containers and play around with them and sort of build from there. So I myself have to sort of think about a migration plan if Singularity Hub goes away. But so yeah, there are registries, and also in the newer versions of Singularity, they also are now Singularity is sort of what is called OCI compliant, Open Container Initiative, and so from what I've read, I have not tried myself, you can actually use, say, the Amazon Container Image Service, the Azure Container Image Service to store your images there as well. So I think it's called ORAS compliant, is sort of the Open Container Initiative's sort of registry standard. You can use basically any registry that is compliant with that standard you can use now. But again, these are sort of the more advanced topics that maybe in future talks beyond this sort of pitch talk we can get into.
So Marty, there was one more about, you started off saying that commercialization is coming. Will we end up in the CentOS stream situation?
Well, yeah, I mean, honestly, yeah. So I don't know, right? So this is, I mean, I'm sort of, I mean, a minor detail is sort of the situation I found myself in this last week. Now, I've learned that, Singularity Hub might be going away, which is kind of a free open service, provided by Stanford in collaboration with Google, right? So Google sort of gave them free nodes to build the containers on and store things in their cloud. And I don't know if those resources are going away, since the maintainer can't, if no one's going to help maintain the service, it's sort of up in the air. But Scilabs, right? It's a paid service, so I mean, maybe we'll pay for storing our containers here now, and it's an open question, I think. I mean, it's how. My impression is if you look at a lot of the features of the more recent Singularities, is they're supporting a lot more of sort of the enterprise aspects that were never really part of Singularity from the HPC aspect, right? And so there is a more hybridization of what Singularity is becoming, I would say. But that's good if it supports Singularity long term, right? If it meets the scientific computing HPC needs for here into the future, that sort of focus on enterprise features and aspects is helpful for us, because you get things like encrypted containers and container verification, which is important in enterprise situations, right? There some compliance issues really mandate that sort of thing, and that's helpful for if those sort of features are helpful for, say, if you have protected data that you need to analyze, right? You could have an encrypted container and run it on any XSEDE system safely. I mean, I'm not super familiar with all the ins and outs of these features, but down the road, I mean, that's the types of features that are being added that could be helpful for the HPC and scientific community. So, but yeah, it's choosing a container platform is, it's an investment in your time and energy, and whether or not, I mean, if it works for your workflow, it's going to be helpful, I think, long term. But which one survives? There's other HPC container platforms. There's something called Shifter, I think was one of the ones. I think that's still being developed. And maybe there's one other one. So there's other ones out there. It's just Singularity was the most popular one and most widely one used, essentially, up until now. So anyway, I'm probably going on too long there. Any other questions?
So there's one that said, how do you compose a reproducible workflow that requires applications from multiple containers?
So there's two answers there. So in the past, so this is sort of my own journey with Singularity, is when I first started maintaining all of the containers that we supported SDSC. For the most part, I had the definition files were completely unique per use case, essentially. So they bootstrapped from a base, say, Debian operating system or CentOS operating system, and installed everything into that one container. Now, that adds like build time, and it's harder to maintain. So for example, like if I had a base container with kind of the operating system and all the sort of utilities that I usually want in it for anything that I'm going to do, say, downstream with different applications, I'd have to sort of keep everything synced up manually, where if I took that base container and then added CUDA to it, I would have sort of a Ubuntu CUDA container, and then an Ubuntu CUDA OpenMPI container, right? And so they were all unique, but they were single build files. Like you only need that one file, and that comes a bit of a problem to maintain. However, I've recently in the last year or so restructured you'll see if you look at my definition file examples, I've restructured things to build off of other containers. So I start with, say, a base operating system container with the libraries and things that I think I'll need for pretty much any other container that I'm ever going to build. And then I start, if I want to have that Ubuntu container with CUDA, then it's like, okay, I point that definition file back to a previous build of that other one. of the base operating system without CUDA, right? And so you it's almost sort of recreating its own sort of layering structure and chaining between definition files to build up the container you want at the end. Or so you could build multiple applications from those different bases. And the one thing that I saw that's really nice in the latest versions of Singularity, which I'm definitely going to look into myself, is with all of this sort of encrypted verification stuff that you can use now. You can actually, part of the definition files, you can actually specify the sort of the signature of the upstream containers that you want to build off of, right? So you could specify in a definition file, like you can only build this definition file from this container if it has that signature, right? And so you can really hard code in a complete verifiable secure workflow if you want to, with the latest versions of Singularity. So which is kind of cool if that meets your use case. Anyway, hopefully that helps answer the question.
Yeah, thanks. We'll make that the last question. A little bit past the hour now. Thanks very much, Marty. Thanks everyone for joining us. We will make the recording and slides available within the next day or two. So have a great rest of your day, everyone.
Thank you.
Thanks, everyone. Have a great day. Thanks, Marty. Great job.
Thanks, everybody.